Greetings and welcome to my new calculus channel. My name is John Gabriel, and today I'm going to talk about three definitions in the mainstream which are evidently ill-formed because they are defined in terms of attributes they do not possess rather than ones they do possess. So let's begin. Now, one of the four important guidelines that I discovered states that concepts should be defined by attributes they possess, not those which they lack. So let me just tell you what those four attributes, those four steps are which are used in determining whether a concept is well formed or not. R is for reification, A is for attributes, C is for contradiction, and I is for independent discovery. So you can read all about those attributes, and I provided a link in an article called "What Does It Mean for a Concept to be Well Defined?" But let's look at these three definitions from the mainstream. So there are more, by the way, but these are just the ones that stick out the most. They're the most painful. So we have an irrational number, derivative, and integral, and they also happen to be pretty important. So let's look at an irrational number. So the way it's defined, or let's say ill-formed or ill-defined in the mainstream, is a number that cannot be expressed as a fraction P over Q for any integers P and Q. Well, it doesn't have to say integers. It can just say rational numbers, because if P and Q are rational numbers, that's sufficient for it to be a rational number. So what they say is an irrational number, what they're really saying is an irrational number is a rational number in quotes with no representation in any radix system. So for example, the constant pi is non-periodic and non-terminating, but any of its partial sums are always rational numbers. So somehow it becomes irrational at infinity. Well, that's just utter garbage, but that's what you have. There is no such thing as an irrational number. It's a myth, okay? And the above ill-formed definition tells us what an irrational number is not what it is, okay? So, by the way, the word irrational comes from a Greek word, alogos, which means it can't be in proportion to anything, really. In other words, to put it as simply as possible, alogos means has no measure. That's what it really means. Not directly, but that's the correct meaning of it. It means has no measure. Okay, so when the Greeks talk about alogos and it's translated into English as irrational, it means there is no measure. So never mind that a number is by definition rational, since it is derived from a ratio of magnitudes. But you have to become very creative and imagine that the rational number is no longer rational, but some magical, unrational number when you get to infinity. So now for our second example, I'm not going to spend too much time on that. The derivative, and I've rewritten this because I tried to use MathWorld's definition, but MathWorld's definitions for derivative and integral were both garbage. They included the word infinitesimal, which makes no sense whatsoever. The derivative of an original function is a new function with the same domain, but with the range consisting of the tangent line slopes of the original function. That's really the definitions. Now, mainstream baboons define it fraudulently as follows, okay? What this here really means is that you have a limit of these finite difference ratios. And so they keep going, and even at infinity here, by the way, if h were 0, and you could rewrite this in terms of h going to infinity, if you say, if you say w over h, where w takes the place of h and h the number of partitions in a given interval. But I think I've covered this before, so I'm not going to spend time on it, but this sequence of finite differences supposedly has a limit that is the derivative. But even in mainstream calculus, the epsilon delta definition is unremarkable, because in order to find the derivative and make epsilon or delta as small as you please, you have to know what that derivative is. And you have no systematic way of finding it in mainstream mathematics, because the first principle methods is bogus. It assumes you already know the derivative. Okay, the first principles method works on this definition. It's pretty circular because it includes knowing the limit before you can use the epsilonics definition. So ironically, none of the finite differences in the above sequence, in this above sequence here, can ever be the derivative. Okay, they can, but the derivative is defined in terms of all of them. All right. So very circular, very ill-formed, because it's defined, as I show you here, if the final h, which is 0, it can't be 0, basically, because if the final h is 0, then this finite difference ratio is no longer defined, right? And there is no such thing as an ultimate ratio. That was just Newton's brain flatulence. And there's no finite difference of this form either, okay, where h actually becomes 0. So all these finite differences define the derivative. But unfortunately, the finite difference that matters the most at the point of tangency is not possible. In other words, something like this is just utter garbage. It's not possible, okay? You don't have it. You can't have 0 over 0. It's meaningless nonsense. Now, the third one is the integral. So a definite integral in the bogus mainstream calculus is the limit of the partial sums of rectangular areas. And if you study calculus, or AP calculus in particular, you'll see something like this. And you'll often see your educators waxing eloquent and doing things like this, where you actually have to know how to find the sums of series. They're not really sums, but the limits of series in integral powers. And that's how you actually get to the limit, which is then the sum of the actual area. So that's not important, but that's what they do, and that's the definition. And then because they, somewhere along the line, they realized that Riemann sums are actually a bunch of garbage, since area is generally defined as a product of two arithmetic means. And by the way, it's very easy to show that a Riemann sum is a product of two arithmetic means, and I have done that. Yeah, and then they came up with this idiotic theory called Jordan measure, which is totally laughable and complete nonsense, almost as bad nonsense as Dedekind cuts and Cauchy sequences being used to define the mythical object called a real number. So as you can see, this product here is one such rectangular area for the value of k. So if we look at these Riemann sums, this is what's happening here, okay? So you've got divisions into little rectangles, as you see here, or it's clearer in this diagram here, where you can actually see that never do these triangles ever represent a true area, which is this shaded area under the curve, okay? They never represent that, and since n cannot be infinite, this has to be defined as a limit. So again, the integral, the definite integral in the mainstream, is defined in terms of all these partial sums, and not the one that matters the most, the one which means the entire area. Okay, so let's get rid of that. And then what happens really, if one had to do something like that, is that you have dx equal to 0. So, you know, I mean, the sum suddenly becomes 0 if you're able to go to infinity, but that's not really what happens. So they're really just looking at the limit. Okay, now, and that's pretty much it. All these concepts are well defined in new calculus, and there's no use of any ill-formed concepts such as infinity, infinitesimals, or the utter garbage of limit theory, which has no place in calculus. And you can download my free article, which helps you determine if a concept is well formed. And that's pretty much it. And there's one last thing here. The areas, the history of area has a lot of information to it. And one of the things that you can use to show, you know, that pi is a product of two arithmetic means is this beautiful applet here. So you can basically trace those lines on a triangle and as follows. And Archimedes did that, by the way. Archimedes triangulated the area of a circle, which means it can also be squared, but not in the same way as using a compass and straight edge. That's cranky. But it can be squared using the method of Archimedes in his on spirals, his work called On Spirals. And so this distance here is the one arithmetic mean, and half of the base of the triangle is the other arithmetic mean. Okay, so that's pretty much it, and I hope you've enjoyed this, and I'll place some more links in the details section and ask you to think carefully about the concepts that you define in mathematics, because the definition of the concepts is the most important thing, and that they are well formed and that they can be used, and new useful concepts derived therefrom. This is a new calculus channel. I'm John Gabriel. Till next time.